Right, let's say we have these two balls colliding. When they after they collide, they bounce off. That's the yellow ball. It bounces off with a certain velocity, say v1, and the green ball bounces off with a certain velocity, say v2. Now, in the case where it's perfectly elastic, so there's no Ke loss, alright, in this special case, we know that the velocity of approach, meaning u2, the speed of approach u2 minus u1, is equal to the speed of approach of when they move up, the speed of separation when they move apart, which is v2 minus v1. So in the equation, we add a minus sign to one side because the two motions are in opposite directions. Okay, right, so that's where we are. What I'm going to do now is I'm going to try to understand how this equation comes about. Now this equation, as I've mentioned previously, comes from doing the algebra, rearranging the equations for the momentum conservation and for the kinetic energy. Okay. Let me try and work this out here. Right, so I have the momentum equation. Let's see, I might need more space, so I'm just going to clear this. Okay, and I'll start by writing down the momentum equation. So the momentum equation is m1u1 for one ball before colliding plus m2u2 momentum of the other ball is equal to, after colliding, the momenta are m1v1 plus m2v2. And for the kinetic energy, we have before colliding half m1u1 squared for ball 1 and half m2u2 squared for ball number 2. Okay, so the kinetic energies after colliding for the two balls will be half m1v1 squared plus half m2v2 squared. Okay, now from this I want to show that these two can be rearranged to get this equation, which says that the speed of separation is equal to the speed of approach is equal to the speed of separation, v2 minus v1, where they are in opposite directions. Okay, so how can we get from there to that? So here goes. Now to make things easy, I'm going to call this equation 1 and I'm going to call this equation 2. Okay, so now I am going to start from 2. I'm going to take equation 2. I'm going to multiply the whole lot by 2. Okay, we multiply the whole lot by 2, all the halves cancel off. So let me do that. So all the half, I'll just cancel off the half directly first. So I'll take this as my equation 2. Okay. Now I'll rearrange this to move all the terms with m1 to one side and the terms with m2 to the other side. Okay, let's try that. So m1 u1 squared, and I'll move this one to the other side. So minus m1 v1 squared. Okay, this is equal to right, that's moved over to the other side, and so I have just m2v2 squared, and I would move this m2u2 squared over to the right, m2u2 squared. Okay, so what I'm going to do next is I'm going to factor out the m1, factor out the m2 here, so that I get m1, and then u1 squared minus v1 squared. Okay, and on the other side, I'll have m2 factored out, v2 squared minus u2 squared. Okay, so this is what I have. Next, I shall expand this. Actually, I shall factorize this, u1 squared minus v1 squared. So that would be u1 plus v1, okay, and u1 minus v1. And likewise, I'll factorize the right side. That gives me m2 v2 minus v2 plus u2 okay, and v2 minus u2. Okay, now in order to proceed, I'm going to show that actually this part, this m1 times this, is actually equal to m2 times this. Now that's quite a jump, and the reason for this is because of equation 1. So what I'm going to do now is I'm going to call this equation 3. I'm going to call this equation 3. This one, okay. Call this equation 3. Alright. Now how can I show that the underlying parts are equal on the two sides of the equation? Well, let me take equation 1. I'll take equation 1. Okay. And I will rearrange this to move all the m1 terms to the right, and all the terms to m2 to the left. So I'll keep the m1 u1 on one side, m1 u1. Now I bring the m1 v1 to the left, so this is minus m1 v1 plus. Okay, and right on the other side, I'll have the m2 v2 come up there. That's m2 v2, m2 v2, and I'll have m2 u2 brought over here, minus m2 u2. Now compare this with the underlying parts. You see, the m1 here and the u1 minus v1. If I take m1 here times u1 minus v1, I actually get this. See, m1 u1 is this, m1 v1 is this. So here likewise, if I take m2 times this bracket to this bracket, I get m2 v2, which is this, and m2 u2, which is that. So that's why, and I got this from equation 1, from there, right? And not from here. So it's from my original equation, original information. So this means that I can cancel this from both sides of this equation because they are the same. All right, I've just shown that they're the same. And then what remains is just this u1 plus v1 and v2 plus u2. Okay, so now I am going to take this equation. I just call that 3 inside. So equation 3. I'm going to take this equation. I'm going to rearrange that. Now, when doing a long algebra, it is always useful to have the end in sight. Meaning that we should, at every step, just take a look at the final thing that we want. Right? This is what we want to prove. This thing at the end. Just so at every step, just take a look and see, if we are there yet, and that would usually give you some idea how to rearrange things. Now, if you look at this, u1 v1 and equals to v2 u2. That's basically what I have left. Now here I have v1 v2 u1 u2. So we have all the same terms. So maybe, just maybe, if I rearrange this, I might actually get this. So let me try. Let's see what I can do. Okay. So maybe I want to have v2 and minus, try and have v2 and minus v2 minus v1 on the right. See if I can rearrange equation 3 to do that. Now I actually have v2 on the right already. I actually have v2 on the right. I have v2 on the left, v1 on the left. So let me bring v1 over. That will be minus v1. So I should move all the rest to the left. So all the rest meaning okay, I have u1 there, I have u1 on the left, and from the right side, the u2, I'll move it to the left, minus u2. So I got this from equation 3. Now, am I there yet? Is this the same as this? Okay, let's take a look. v2 minus v1 on the right, v2 minus v1 on the right. Okay, brilliant. One side is exactly right. On the left side, I have minus with the bracket of u2 minus u1. Now on this equation, I have minus u2 plus u1. Actually, they are the same. If you remove the brackets here, with a minus sign outside, you need to change the sign of each term inside, right? Change the sign of u2 and the sign of minus u1. And this is exactly what you would get. So therefore, from this step, I can say that this implies the equation that we want to prove. All right, the equation that the speed of approach is equal to the speed of separation, with the minus sign to tell us that they are in the opposite directions.